Okay, I appear to be live. Let's find out if anything is working. Hello. This is a very long delay, which makes me kind of unsure. I think you may have misread what I said. Let's close this before it echoes. Oh, someone's beat me to it. My audio is pretty quiet. How do I fix that? Oh. Hello? I mean, is this any better? Okay, that's good. On OBS, you can increase the volume of your mic. I don't know, I've just decided to move the microphone closer to my mouth. That's a good point, Max. Oh, thanks. I like my background. I think it's from Firewatch, so it is literally lit. Okay. I think I'll give people a few more minutes to filter in. I unfortunately don't have any takeout stories to share with you today. Let me see. What interesting takeout things have happened? I don't know. Wow. Wow. Amazing. Hey Kevin, want 3 ACIO problems if you update the Gutenberg parser to read from the CMS score spec? I have no idea what this sentence means. I did not in fact know about this fireworks thing. It isn't the same every time. I thought it was. Okay. Yeah, I work on Google Photos. I don't know anything else about Google. I can definitely look into whatever it is you're trying to get me to look into with respect to the Gutenberg parser. Okay. I think it is time to get started with the lecture. You might be able to tell already, but my voice isn't the best today. I've been a little bit sick, but I'm here to deliver you a lecture anyway on divide and conquer and Centroid decomp. Okay, so let's get started. Time for a motivating problem. Oh gosh, I've forgotten how to use this. You have an array. You would like to count the number of inversions in this array. So let's say your array is something like this. We say a pair of elements in the array are inverted if the bigger number comes before the smaller number. So in an array that's sorted, there should be no inversions. So the sorted array would look something like this. And in an array that's sorted in reverse order, something like this, then there'll be lots of oh no. Oh gosh. How do I undo that? Okay, I've messed everything up and we're only 3 minutes in. Oh, this is going to be a great lecture. Okay, so a pair of elements is inverted if... I've done it again. A pair of elements is inverted if the smaller number comes after the bigger number. So for example, the 3 and the 2 here, these are inverted. And another example is this 7 and this 1. These are also inverted. The reason you might care about inversions is because the number of inversions in an array you can kind of think of as a measure of how sorted it is, because a perfectly sorted array will have no inversions and a reverse ordered array will have the most inversions it possibly can. So the question we're trying to answer is, how do you efficiently calculate the total number of inversions in an array? Okay, does the problem make sense so far? Somebody is typing. Maybe. I can't think of which IOI problem you're thinking about, but this is like a classic problem in computer science. Okay, so I guess if you're solving this problem without knowing the title of this lecture, a pretty simple thing you might try to do is to say, okay, well, right. Well, what I can do is I can sweep from left to right, and as I consider a new number, I can try to figure out how many numbers to its left are bigger than it, because each number that's to your left and bigger than you are counts as an inversion. So maybe if I get a more complicated example, something like, I don't know, something like this, for example, then you know that, I'm going to make this mistake every time, aren't I? Then you know that for this 3, all the numbers that make an inversion with it to its left are the numbers that are bigger than it. So 5, 7, and 9. And not 3 because it's equal. Okay. So basically, what the data structure you're trying to build here is you want to be able to, as you sweep from left to right, you want to maintain the current set of all the numbers that you've seen so far, a multi-set actually, and you want to also be able to efficiently say how many numbers in this multi-set are larger than this given number. So if you are familiar with your policy-based data structures, that should be a very simple problem. And if you're not, you can kind of do this offline using a range tree. So as a general sketch of the idea, what you can do is you have a range tree that you have a range tree over the set of values that you have. Every time you encounter a new number and you want to add it to the set, you kind of increment that position in the range tree by 1. So for example, if your range tree was I don't know, here is a very rough representation of a range tree. To add a 1 to the range tree, you increment, so everything is 0 initially. To add a 1 to the range tree, you go to index 1 and you increment this value by 1. So this is now 1. To add a 3, you go to index 3, which is 0, 1, 2, 3. You increment this by 1, so that's now 1. And you can go on incrementing everything by 1 to add it to the range tree as you go. So I guess 5, 6, this is the next one, which is 7, and then this becomes 1, and so on. And maybe let's say we get to this 3 here. That means we go to index 3 and we increment this by 1, so that becomes 2. And to query the total number of elements that are more than a given number is pretty simple. It's just a sum query over some suffix of this range tree. Yeah, so that should be a fairly straightforward solution if you understand your range trees. If the numbers are in a relatively small range, then you can just build a normal range tree. But if the numbers are, by small I mean up to, like, let's say like 100,000. But if the numbers are getting really, really big, then you'll end up having to create a lazy create range tree because, you know, this tree might be really, really big. Or alternatively, you can kind of compress the input so that you can compress the input into the range from 1 up to n, because all you care about is the relative comparisons between these numbers. So for example, if your array was something like 3, 1070, well, that's really just the same as if the numbers are 1, 3, and 2. Because relatively speaking, 3 is as much, 3, 70, and 1000 have the same relative ranking as 1, 2, and 3. So that's how you might be able to get around this. Okay, so this is a fairly straightforward solution, and you might be wondering, Kevin, why are you telling me about this problem? This seems to have nothing to do with divide and conquer. To which I would say, the average human tongue has a surface area of 12 square centimeters. And you would respond, what? Okay, so we are interested in divide and conquer. Therefore, let's pretend that this solution doesn't exist, and we'll look at an alternative idea instead. Okay, so here's the idea behind divide and conquer. I don't really know how to motivate it, so I'm just going to tell you. So when you're trying to count the number of inversions, it's kind of complicated because there's like order n squared pairs of numbers. There's like order n squared pairs of numbers that you have to consider. And trying to consider them all, each pair individually, is going to be really slow. So what we're going to do is we're going to cut the array in half. Could probably make this a lot bigger. This is really slow, but that's okay. let's take this array that we have and let's get rid of. Oh, that's not what I wanted. Dang it. Okay, whatever. Let's have a new array. Okay, something like that. What we're going to do is, as implied by the name, we're going to divide this array in half. Sure, we're going to divide this array in half. And what we're going to do now is we're going to count the number of pairs of elements that are inverted, where one of the elements is somewhere on the left of this divide and one of the elements is somewhere on the right. And once we've counted all of the pairs of elements that kind of, I guess, cross this dividing line, what we can do then is we can recurse into each of the two sides and count them individually. So we can recursively solve the problem on that array and recursively solve, and by solve I mean count the number of inversions on this side, like that. So my final answer is going to be the number of inversions that cross this dividing line plus the number of inversions in this array plus the number of inversions in this array. And in doing it this way, we actually end up counting every possible pair of inversions, because an inversion kind of has three possible cases. Either both the elements are on this on the left side of the divide, in which case we'll count it here. Both the elements are on the right side of the divide, in which case we'll count it here. Or there's one element on each side of the divide, so we'll count it in here. So that's a really nice way of solving the problem, isn't it? Well, first let's figure out how quickly we can, first let's figure out how fast this is, ignoring the problem of having to count this. So let's say that we can do this count here, in linear time. Now, when we divide and recurse, we have to solve each of these problems separately as well. But if we can solve both of these in linear time, you can see that in total together, you can solve both these problems in linear time, because sure, you have twice as many problems, but they're half as large, so they'll take linear time as well. And again, when you divide this further into 4 sets on each side, now you have 4 subproblems to solve, but each one is only a quarter of the size. So again, you can solve all these in total in linear time. And the total number of times that you can halve the size of these arrays is log n. So in total, there are a log of these levels. And each of these levels you can solve in linear time. So in total, this whole process will take you n log n. So this isn't, n log n is pretty good, and it would match the time complexity of this range tree based solution that I showed up here. But still I have to go through the detail of how exactly you can do this count in n log n. Do this count in order n. Okay. So let's take another look at this subproblem here. Let me just copy this. And then we have the dividing line thing here. So let's formalize exactly what we're looking for. We're trying to count the number of elements, the number of pairs of elements where one element is on this side of the array, one element is on this side of the array, and the element on the left is, I've circled the wrong things. And the element on the left is actually larger than the element on the right, because that counts as an inversion. So what we can do is you can say, well, if I took all the elements on the together and I sorted them and I recorded which side of the array they came from, so it would be something like let's say this side is the red side and this side is the purple side, then your array would look something like there'll be a 2 here, there'll be a 4, then 8 and 9 would be at the end, and red, this would be a 1, 3, 6, 7. Don't you have to merge sort anyways? I guess that's kind of where we're headed. Yeah, so if you kind of combine these two sides and form this array here, then for each of these elements on the right side, the number of inversions is simply the number of red elements to its right. So this 2 is going to form an inversion with these 3 things. This 4 is going to form an inversion with these 2 things, 6 and 7. And this 8 and this 9 don't form any inversions. So once you do this initial sort, then you can quickly sweep over the sorted array, and keeping track of the total number of red elements you've seen so far, you can calculate how many of the purple elements form an inversion with the red elements. I've chosen 2 very similar colors, so I apologize for that. Okay, so does that idea make sense so far? So if you do this naively, this sorting step would take you order n log n time. So in total, because there are log n of these levels, then the upper bound for the time complexity here is actually n log squared n, which might be okay for some problems, but we can do a little bit better. The quickest fix you can do is, instead of doing a normal n log n sort here, you could maybe try to do a count sort, but things get kind of complicated when you recurse. You kind of have to compress things, and that's a bit annoying. So what you can do instead is you can kind of do a merge sort-esque idea. So I guess the way that I presented this so far is you calculate the number of inversions that cross the line, and then you split and you recurse into both these halves, and then you solve the problem recursively. But we can do it in the other order. So we can recursively solve the problem in each of these halves first, and then we can use that to more efficiently find out the answer for this half. How does that work? Well, remember down here how in order to find the number of inversions using this method here, we ended up having to sort the array? Since we've already done the work of sorting this left half and this right half, can we combine them into a sorted array, into the sorted array for both halves combined in linear time? And the answer is yes, you can. And you do that using a fairly straightforward merge sort. So from the left half, you would have an array that's something like 1, 3, 6, 7. And on the right half, you would have an array that's something like 2, 4, 8, 9. And to combine these, you just have a pointer that starts at the that starts at the start of each of these arrays. And whichever number is smaller, that's the next element that you put into your sorted array, sorted combined array, and then you shift the pointer along. And you keep on comparing the current position of the pointer in each of these arrays and taking whichever one is smaller, chucking it into your combined sorted array and moving it along. And in this way, you get this merged sorted array in linear time. Okay, so that's basically the idea for how you count inversions using divide and conquer. You, to summarize, split the array in half. You count the number of inversions that are in the left half of the array only. Count the number of inversions that are in the right half of the array only. And because of the process that we used for counting these inversions, we end up with a sorted array on the left and a sorted array on the right. And you can combine them to create a sorted array for the left and the right combined. And you can use this combined structure to count the total number of inversions that cross this line. Every inversion either crosses this line or doesn't, in which case, if it does cross the line, it'll be counted in this step here. If it doesn't cross the line, it's counted in one of these steps on the left or the right. And that's kind of the basic shape of all the divide and conquer problems that we're going to be discussing today. Or it's I guess the basic shape of what a divide and conquer solution looks like. You divide the array in half, count the solutions that kind of cross this divide, and because you've considered everything that's crossed the divide, you now have a nice simpler problem, because you know that all the remaining things that you care about either lie completely on the left, in which case it's isolated from everything on the right, or it lies completely on the right, in which case it's isolated from everything on the left. So you can divide the problem and consider these two halves completely independently from each other. With regard to the merge sort you just described, can we just sort any array, therefore in order n, assuming that we allocate sufficient memory beforehand, and then partition it in half? I'm not sure what your thought process there is. But the problem is that in each half of the array, you still have to do order n log n work, where n is the size of that half of the array. I guess if you write out the recurrence relation, it would look something like this. So the amount of work that you do for an array of size n is equal to the amount of work. So you split the array, so there's two halves. Each of those requires you to sort an array of half the size, and then you add on the linear time step of combining the two. So this is kind of the relation that you end up with. And I guess if you expand that, then you get order n log n, which you can do analytically, or I prefer to think of it in this kind of geometric way, where I guess the first layer requires you to do order n work. This is size n. The next layer requires you to do two sets of size n on 2 work. That's n on 2. And the third layer requires you to do 4 sets of n on 4 work, and so on. And the point is that each of these layers requires you to do order n work. The number of layers is log n, because after you've split things up log n time, you end up with single elements, which you can do in constant time each. This is log n. Yep. So you can kind of think of this as like a as a rectangle whose width is n and whose height is log n. Okay. Hopefully that answers your question. Why is it necessary to count the inversions on each half? So when we kind of do this step here of splitting the array in half, and there's kind of three cases for where the inversions are. Either the inversion, one element of the inversion is on the left and one element of the inversion is on the right, in which case the process I described here will count that inversion. Or the inversion is, both elements of the inversion are on the left, or both the elements of the inversion are on the right. So for all of the inversions where both the elements are on one side of this divide, then you're not going to count them when we do this dividing step. So we would effectively be undercounting our answer because we're missing some of these inversions. That's why you have to recursively solve on each of those sides. Hopefully that makes sense. Feel free to tell me if it doesn't. Okay, cool. Glad I could clarify that. Set the halves. Okay, some more discussion about the merge sort stuff. You can solve inversion counting in linear time. Wow, that's not something that I knew. I guess I'll leave that as an exercise to the reader. Base case, T of 1 equals order 1. Is that true? Oh, I guess you're just saying that it's constant time once you get to a fixed constant size. That makes sense to me. Man, I don't know if you can count this in linear time. It seems like a result that would be contradictory to some kind of theorem in computer science. But I don't know, so I guess I'll believe it. I mean, counting inversions sounds like it would in some way be equivalent to sorting. Oh, you said linear is in fact impossible. Oh. Okay, in which case I'm not confused anymore. Alright, hopefully no one else is confused. So, and everyone understands this problem entirely, in which case I'll move on to the next problem. I don't want to do that. Okay. Okay, new problem. So again, we have an array of it's an array of integers. They might be negative. And you want to be able to count the number of subarrays, contiguous, that have some, at most, k, for some fixed k. So I guess, for example, if you have an array that's like, I don't know, this, and k equals, let's say, 5, then this subarray would count as one that has sum at most k. This subarray as well. Yep. And I guess, all the subarrays, oh, not that one though. All of these subarrays of size 1. And I think that's it. Yeah, so in this case, there would be 6 subarrays. Kevin would support this method of proof. My favorite method of proof is exercise left to the reader. QNED, FlexiLatin. Oh, there's a whole bunch of words here and they're very confusing. Okay, so hopefully the problem is clear to everyone. Okay, so I guess your first thought is, dang, that kind of sounds like a hard problem, but maybe I can solve it in some way. You can kind of take a similar approach to what we did in the first solution I gave, and that's to say, okay, there's a lot of subarrays I have to consider, so what if I fix like an endpoint? Maybe this is going to be, I'm going to count all the subarrays that have sum at most k, the end here, and see how many possible starting points would fit my description. So one difficulty that you kind of have with this is some of the numbers are going to be negative. If all the numbers were positive, then you could do a fairly simple binary search, but because you have negative numbers, things get a bit complicated. Yeah, that's basically it. So what you can do is you can kind of calculate all the prefix sums for the array. So for example, I'm going to draw the prefix sum as if it were a line graph. So the first prefix sum would be 1, the next prefix sum would be 4, then it jumps all the way up to like 11, then jumps back down to negative something, and then jumps back up again. So now that we have this kind of line graph representation, hopefully that representation makes sense. If not, feel free to shout at me. The question that we are asking here before is basically, all right, if this is going to be the end of the subarray we're considering, how many of the starting points to my left would form a subarray of sum at most k? How does this representation work geometrically? You want everything. You want to find all the points that are kind of inside this rectangle, I think, where this is height k. Is that how that works? Let's see. So the value here is 7. And the value here is like, isn't it k below inf up? I think you're right. Okay, let me redraw this because I'm just confusing myself. So, every time. Okay, I guess the lines don't really matter, but what matters is kind of the points. So here's like the, I guess, the value of your prefix sum over time as you go to the right in your array. And let's say that we're considering this point right here. So let's say that we're looking at the contiguous subarray from here to here. So this is kind of the end point, I guess. So the total sum of this segment would be this minus this. Oh, so it would be negative. Okay, so I guess I've viewed this upside down. Okay, I understand now. Okay, so I guess if we were considering this range instead, and this was kind of the end point, then the total sum of this subarray would be the difference between these two. Well, I guess this is actually the subarray ending here, because the way that prefix sums work is that it's inclusive of this end but exclusive of this end. But I hopefully that kind of explains the idea okay. So yeah, if you want the sum to be at most k, then you want this distance to be at most k, and anything kind of above here is fine because this is where the sum is negative. So I guess to summarize, what you're trying to do is for each of these points, you want to count the number of points that are inside like this rectangle, where this extends down by k and this extends up by infinity. And as someone mentioned already, you can of course solve this again using a range tree and a sweep. But we're not interested in those kinds of solutions, are we? We're interested in divide and conquer-esque solutions. Okay, so I guess we will go back to, I don't know, I'll just have another example. The numbers aren't all that important, I don't think. Okay, so again, like in the previous idea we had, we're going to split this array in half, and we're going to say, okay, I'm going to count all of the subarrays that have a sum at most k, where the left end is somewhere on this side and the right end is somewhere on this side. So basically it's all of the subarrays that kind of intersect this cutting point that we made. And again, the reason that's useful is once we've counted all of the subarrays that cross this divide, then we can recurse into our two halves like this. Recurse into our two halves and count the number of subarrays that have sum at most k on the left side and on the right side, and they'll be completely independent of each other, and just add up the three answers that we get and we'll get the total sum, the total number of subarrays that have sum at most k. And for the same reason as we described here, I guess, the total complexity is going to be order n log n, assuming that we can do this count in linear time. So I guess the key question really is then, how do we do this count in order fast? Okay. So what you can do is you can say, all right, kind of the key difficulty, I guess, with this approach that we had up here that requires a range tree is that our queries are kind of all over the place. Like, this query here has this range, and then the next query has like a lower range, so something like, something like this, and then the next query again has like a higher range. So the range keeps jumping up and down over time. It would be really nice if we could kind of sort them and go with them in increasing order. But the reason that we can't do that is because we have to sweep from left to right as we keep introducing new points. But if we divide the array in half like this, and we consider counting only the things that intersect this middle point, things get a lot simpler for us. And the reason is because I'm not sure what diagram exactly that I want, but I'm gonna make this a bit bigger so that things are kind of nicer for us. The numbers don't even matter, I should just make them up. Something like that. And the dividing point is like here-ish. So if we're considering, let's say, the subarray ending here, we know for sure that we're going to include all these elements because we're considering only the subarrays that cross this position. And so if we take the sum of all of these, maybe it's like, I'll just make something up. Maybe it's like the sum is 6 and k equals 10 in this case. So what you're looking for then is all the subarrays on the right side that have sum less than or equal to 4. And the nice thing for us is that for each of these queries that we have to do, so maybe the next query is going to be this one, which has sum like 3 instead of 6, and this query which has sum 26, the set of possible candidate ending points we have never changes. So we can create a static offline structure over here. Whereas in this solution that we had up here, we couldn't do that because as we swept from left to right, the set of candidate points keeps growing as we add more as we sweep. So when you're, I guess, building a divide and conquer-esque solution, this is kind of the thing that, one of the things that you're exploiting that makes a divide and conquer solution work sometimes and a not divide and conquer solution not work. In this case, you can find a workable solution in the non-divide and conquer approach, but it is in some sense more complicated in that you need a more difficult data structure to track. Okay, so what we're going to do then is we're going to create a set of all of the possible, I guess, suffixes up to this dividing point. So for example, in this example, we have like 4, -4, then it's like -11, -8, -7. And this is really annoying because they're not in sorted order, so we can sort them. So we get something like -11, -8, -7, 4. Right. So we can sort all of these suffixes, I guess. And this makes it a lot easier to query over. And so what we can do now, after we've created this sorted set-like structure. It's actually probably just a vector. For each of these queries, do you have to sort these queries as well? That's one I'm not sure about. I guess you kind of don't really have to. Anyway. Okay, so for each of these, you get the prefix sum, 26 or whatever. And all you have to do is to find, if I were to combine this prefix with one of these suffixes, what do the values have to be in order to keep me the total sum less than or equal to 10? You need the sum to be less than or equal to negative 13, because 26 is already bigger than k, so you need this side to have a total negative value big enough to offset that. So all you have to do is to find in this array where negative 13 is, in this case it would be like here if it existed, and just count all the number of elements that are to the left of it. So in this case, there's 0 elements. That would work. Let's take a more interesting example. Maybe you find a range whose sum is, what would be an interesting number? Let's say 12. So that means that because k is 10, you need the total sum to be less than or equal to less than or equal to negative 2. So negative 2 would be here-ish in the array between this 4 and negative 4. So you know that all of the suffixes on the left side that would work are the ones that are to the left. So in this case, there will be 4 possible matches for this hypothetical prefix that we're considering. So if you do that for each of these prefixes, then you get the total count effectively. So as an implementation detail, I guess you could do this with a set, or you could just do this with a binary search, and maybe you need to do a little bit of bookkeeping to efficiently count how many elements are to the left, but you can work that out. So this approach is order n log n, because you have to sort the prefixes on the left and the prefixes on the right. But I guess in the same way that we had this merge sort-esque thing in the first problem, you can similarly do a similar calculation to more effectively compute this structure without having to sort it, without having to do an n log n sort. In practice, I don't know how much time you actually save by doing this though. I imagine that an n log squared n is going to be pretty fast anyway. So I don't think I would bother doing it in a contest. But who knows? Maybe I'm wrong. So I guess, does this idea make sense? Are there any questions? The seg tree solution is more mind-blowing. Yeah, if you haven't seen this particular set of ideas before, it's pretty cool. But as a demonstration of divide and conquer, I think it's pretty nice problem as well. Okay, if everyone is happy with this problem, then I guess I'll move on to our third problem. Okay, So this problem has a slightly different flavor to the other two problems. So in this problem, I give you a set of points in the plane. Just to make your life a bit easier, I'm going to guarantee that they all have distinct coordinates, so there's no two points in the same row or in the same column. And my question to you is, how many pairs of points are there such that the rectangle I draw between them, if those 2 points are corners, have a rectangle that is completely empty? It's already been an hour? Oh my gosh. This wasn't supposed to take this long. I still have to go through Centroid decomp as well. Okay, maybe I'll speed things up just a little bit. Okay, so yeah, you have to count the number of pairs of points that form a rectangle whose interior contains no other points. And because I made the points have distinct coordinates, you don't have weird annoying cases where points are on the edges and stuff. So it makes things a little bit nicer. So your first thought might be, wow, this doesn't seem like the other two problems we discussed. Can you really apply divide and conquer here? And the answer, like the other two problems, is that there is a non-divide and conquer-esque solution. But for the sake of brevity, I'm going to ignore that this time. So your first thought is probably, how exactly are we going to divide this in the first place? And the answer is pretty simple. We're going to find the vertical line that we can draw such that half the points are on the left and half the points are on the right. That's kind of nice. So what exactly is the question we're trying to solve in using this division? We're going to count the number of rectangles that we can form such that one of the points is on the left and the other point is on the right. To make the problem a little bit simpler, we're going to assume that the point on the left is always the top right corner, and the point on the right is always the bottom left corner. After we've calculated the solution for this variant of the problem, all we can do is flip the points vertically, and solve the problem again, and that will get us all of the rectangles that have the points in the opposite corners of the rectangle. So like that. Okay, so now that we've said that, we can just assume all of the points are on the top right and bottom left. And by top right and bottom left, I actually mean top left and bottom right, I think. Thanks for that. Yeah, I mean, I drew it, so I'm sure you all understand. It's because I get really confused because some problems use coordinate systems that are like this, and so you have to flip things around in your head. But sometimes they use coordinate systems that are like this instead, which is the one I prefer. Anyway, I'm just apparently very tired. Okay. So now that we've established the shape of the solution, I guess for completeness sake, after we've counted all of the rectangles that cross this dividing line, then again you can recurse into the left half and the right half, and then count all the rectangles that do not cross this line, and they're going to be independent, and all rectangles fall into one of these three categories. Either they cross this line, or they fall entirely in the left, or they fall entirely in the right. Okay, and for the same reason as the other two problems, this is going to take order n log n time, assuming that we can efficiently calculate these crossings. So let's look at that now. Okay, here's our dividing line, and there's some points on the left, maybe something like this, and there's some points on the right. So I guess the question is, how are we going to calculate all of the rectangles that cross this line and don't contain any other points? Well, the nice thing about this dividing line is that we know that all of the rectangles we're considering for these points definitely have a width up to this line at least, and then beyond it to actually reach one of these points. And it's going to extend down some amount. So if we're just looking at kind of the left side and pretending that the right side is irrelevant at the moment, then all of our rectangles kind of have exactly this same shape, where they extend down by some amount and then they go right. And the amount that you can go down is simply limited by whichever point below you. The first point that you can find below you that is closer to the line than you are. How do you calculate that efficiently? Well, what you can do is you can kind of you can sweep from the bottom upwards and maintain a sorted stack of these sets of points based on how close they are to your dividing line. So initially you put this point on, and you know that I guess this point can like extend down as much as it wants because there's no other points for it to intersect with. Then the next point, because it's further to the right, you know that it's limited by this point here, which is to its left. And then when you consider this point, because this point is actually closer to the line than your previous point, you can kind of just get rid of this point from consideration. The reason is because, well, this point extends down up to here. And for any other point like above it, you know that it can only extend as far as this line. I didn't explain it very well. I guess because this point is closer to the line than this point is, you know that this point is the limiting factor, because any other like point up here, if it were going to be limited by this point here that you're considering, you know that it will get limited by this point too. So this point here is redundant. So I guess if I were to draw this more succinctly, yeah. I'm a bit confused. What is happening here? Yeah, you have a sorted stack of points where as you go up towards like the upper side of our set of points, the points are further and further to the right. And the moment you find a point that is further to the left, then you start getting rid of points until you only have a set of points that continues this structure. The structure of as you go up, the points go to the right. So you have that. And when you get to this point here, this point kind of dominates these other 3 points that we have here. So we kind of delete them too. And you're left with this. So in that way, if you keep this sorted stack of points, you can efficiently work out for every point how far down we're allowed to extend before, oops, this is actually that one. How far down we're allowed to extend for each of these points before we hit another limiting point. Okay? So hopefully that makes sense so far. So what we're eventually left with is a bunch of queries. Each query says, all right, in this particular, gosh darn it, just let me select this. Query is a given range. How many points could I match with in this range? It's like you have a bunch of these like partial rectangles. You want to know how many points you could match with inside this range. And these ranges might overlap. So how do you answer this question? Well, firstly, let's consider, I guess, dang it. Okay. Let's consider one of these points we're considering. This is kind of the range of rectangles we're allowed to consider. What points can we match with? Well, any rectangle that is between like this upper limit and this lower limit, we could form a rectangle with this point. So for example, this one, or this one, or that one, so on. You can form a rectangle with any of these. But the problem is that even though we know that this left side is completely empty of points, so as far as we're concerned on this left side, any of these rectangles are valid. The problem is that not all of these rectangles will be valid according to the right side. So what set of points actually works for us on this right side? Well, on the left side, in the similar way that we had a sorted stack, we have a sorted stack on the right side as well. So the way that you can think of it is, let's consider like the topmost point that's underneath this limit that I set here. Maybe this one. You know for sure that this rectangle is empty because we said that this was the topmost point, so there can be no other points here. Now the thing is that this point here, it's going to invalidate any rectangle that involves points like inside this particular section. Because for any point who is in like this area, it's going to contain this point in it when you draw the rectangle like this. So you know that every point, for any point to work, to form a rectangle that's empty, it's got to have an x coordinate that's further to the left. So like here, or here, or here, or here, and so on. So if we consider the next point that matches this description, by a similar argument, we know that it rules out every point inside this range as well. Like that. So again, the only points that are going to work are the ones that have an x coordinate further to the left. So essentially what that means is, as you kind of go down, the points that you're allowed to intersect with have to keep getting further and further and further to the right. These 2 points are invalid. It would have to be something like this. So it's like this set of points that we're looking at has to get further and further to the left. Sorry. As you go down, the points keep moving further to the left. So you can see again, this forms a sorted stack. Just like we had down here, we had that sorted stack of things that we were looking at. We kind of have like this inverted sorted stack that we're considering over here. And it's kind of interesting that both sides of the divide, we end up looking at a sorted stack. And in some sense, that kind of makes sense because the problem on the left is kind of just, the left and the right are pretty much symmetrical. If you just flip them so the right was on the left and the left was on the right, the problem would still be the same. So it makes sense that there's kind of the symmetry in the solution. So what do you actually end up needing to do? Yeah, so putting this all together, what we're going to do is we're going to sweep from bottom to top on this left side. Remember, we have a whole bunch of these queries that we pre-calculated. And as we sweep from left to right, we kind of maintain this sorted stack of potential candidates that we could connect with. And I guess as you add new points, you end up having to get rid of old points that end up too far to the right and get, I guess, dominated by this new point. And maintain this like sorted stack of points. And to actually query this sorted stack, all you have to do is to find, I guess, how many elements are there in this particular range. And one way you can do that is either through, is the stream okay? One person says it's fine, the other person says it's not fine. Okay, I'll assume it's just a transient internet issue. Yeah. So I guess reiterating what I said, in maintaining this sorted stack of points, each query is just a question of how many points are there in the stack inside a particular range. And the nice property that you have is that because we're sweeping from bottom to top, each time we have a new like query point, it's always going to involve some top X elements of the stack. This is like the top of the stack, I guess. And this is like the bottom. And so if your stack is implemented as a vector, you can just binary search for the corresponding lowest point that's still within this query range and get your answer from that. Hopefully that all makes sense so far. So this approach is order n log n, because we have to do this sort and then sweep and then a binary search, but they're independent. So in total, if we factor in the cost of divide and conquer, this will be an order n log squared n approach in total. So how do you turn this into order n log n? For the sake of brevity, I'm going to leave it as an exercise to the reader. But basically, you have to exploit the fact that these query ranges that we're making, they're not arbitrary. As the like upper range moves upwards, the lower range will also move upwards, I think. Now that I think about it, that's not true, is it? I'm not sure. Exercise left to the reader, I guess. Or maybe it's just not possible. Who knows? So yeah, in summary, that's how you can solve this problem in n log squared n. Okay, are there any questions about this particular problem? If not, then I think that's all that I had to say about divide and conquer as a technique. So in kind of the problem sheet that I linked earlier, There's a whole bunch of problems that you can solve without divide and conquer, and usually better than the time and complexity that divide and conquer gives you. But those problems are still really good practice for, I guess, implementing the divide and conquer strategy. There are only a couple problems that I actually know that don't involve that you have to use divide and conquer to solve, and they're all kind of like really good involved problems, and I don't want to spoil any of them. So here's a bunch of problems for you. Okay, so I think we'll have a quick 5-10 minute break, so I can go get some water or something, and then when I return, it'll be time to go through Centroid decomposition. You could mention how D and C can be used to do queries. Yeah, I guess all three problems that I've showed you so far have been about counting things. But I guess you can imagine how they can be used to solve optimization problems, where you're trying to maximize something. So instead of being like getting the total number of things here and adding together the total number of things in each of the two halves that you recurse on, you can do other things other than add them together. Like maybe you're trying to find the best solution, so it's like a max. Or you can use it to solve offline queries as well. I mean, I don't have any particular examples except for Scooch Hop. So I mean, I guess I'll just explain the general idea. So let's say you have some kind of problem that's on an array, and you have to answer questions that are kind of the form, I don't know, it's like some query over in a range, answer some kind of thing. So it's like a bunch of range queries. So something like this, I don't know. Now, if the problem is offline, you can apply the same kind of divide and conquer strategy, where you say, all right, I'm going to divide like the I guess the query space in half like this, and I'm only going to answer the queries that they only answer the queries that intersect this middle point that I created. Why is this useful? Well, it means that you can kind of pre-compute something on the left side for all of the, I guess, suffixes of the left side of the array up until the cut point. Pre-compute something for all of the prefixes on the right side. And then each query is a combination of one suffix on the left side with one prefix on the right side. And if this problem is easier than answering, I guess, the general problem of just queries everywhere, maybe combining these prefixes and suffixes make it somehow easier, because whatever pre-computation you now have to do is A, offline, and B, they're all either suffixes or all either prefixes. Maybe this combination step can be easier. And of course, once you've answered all the queries that cross this line, you can kind of recurse and answer all the queries that fall wholly in the left side, and recurse and answer all the queries that fall wholly on the right side. Yeah, so that's the general idea of solving offline queries in this way. 3D range query is a good example. Range query. Okay, I guess I see the kind of the shape of the solution there, but it sounds kind of disgusting. I don't want to go through it. But yeah, that's the general idea of this offline query approach. If anyone has any straightforward problem that involves this, that would be good. Although I think actually one of the problems that Quang linked me is like that. I don't know if you remember. Send like 2. Both of them are like that. Okay, I've moved the 2 problems that you sent me into another section of the problem sheet. I haven't actually looked at them, so maybe they're not what you said they are, but I'll assume that you're telling the truth. Okay, I'll be back in a few minutes. Okay, hopefully you all had a wonderful break. So yeah, I guess let's get on to Centroid decomposition. What was I thinking about? Oh wow, there's a lot of stuff that's been happening. Are there any questions that were aimed at me that I've missed? If the answer is no, then I guess don't say anything and I'll assume that everything is fine. Oh no, someone is typing. Oh, they've stopped typing. Now someone else is typing? Okay, if something pops up, then I'll assume, then I'll read it and answer it. But otherwise, I guess I'll just move on to centroid decomposition. Okay, so I guess the problems we've been looking at have been of the form, you have some kind of question over a set of objects that you want to consider, but there's like really a lot of them. So in the first example, where we're counting inversions, you have to consider pairs of indices. So there's like order n squared of them, so counting them all is kind of difficult if you want to enumerate them one by one. Likewise, in the second problem, there's order n squared subarrays, so enumerating them one by one is also really slow. And the third problem, it's like there's order n squared pairs of points that you have to consider, which is really a lot of them. And the way that we've kind of simplified that is by saying, all right, what if we can draw some kind of like common structure and consider only the set of objects that intersect, that have that common structure in common. So what does that have to do with centroid decomposition? Well, let's motivate it by another problem. This problem might be sort of familiar if you've been taught centroid decomposition before. The problem is this. I give you a tree. It's a weighted tree, so these edges have some weights associated with them. That's a terrible 7. And my question to you is, does there exist like a path in this tree that has weight exactly k? So for example, if k equals let's say 22, then the answer is yes. This path here, oh crap, you didn't hear that? Maybe if I make the pen a bit bigger. This path here has a total weight of 22. So the question is, given a specific k, can you find such a path in the tree? So I guess again, in a similar way that we've been thinking about the last 3 problems, is, dang, there's like so many paths I have to consider. That sounds really annoying. What if I can find some kind of common element? Well, the thing that people really like doing is rooting the tree. So let's say, I guess, we pick this vertex here to be the root of our tree. So if we root the tree here, and just like in the other problems where we said, let's consider all of the, I guess, rectangles that intersect this line, or all of the subarrays that intersect this line, or all of the indices that cross this particular line, pairs of indices that cross this line. Let's consider all of the paths that start on one side of the tree, go through this central point that we've chosen, and end somewhere else. And the question is, are there any paths of that form that go through this special vertex that we've chosen that have weight exactly 22? This problem is this question is a lot easier to answer, because the only thing that we care about is because it lets us say, okay, we're trying to find, I guess, two sections, I guess. Let's say something like this. Yeah, something like that. Two sections where the total sum, the sum of like one half of the section plus the sum of the other half, is exactly 22. So how do you do that? Could we just do a pre-order traversal on the tree and then run a two-pointer trick on the flattened array? Maybe, I don't know. I've no idea what's going on here, but it seems not relevant to what I'm discussing at the moment. Okay, so what we're going to do is we're going to say, all right, let's root the tree here, and let's consider all the different path lengths that start at some node and then end up at the root. So for example, if we had something like this, something like that, let's say, then if we started here and went to the root, that would be a path length of 2. If we started here and we went to the root, it's a path length of 5. And we're just going to calculate that for each of the vertices of the tree. Anyway, there's a lot of them, but I'm sure you get the point. And so what we're looking for then is we're looking for a pair of these indices, I guess, whose combined sum is exactly k. So in this case, these two, 17 plus 5, would make 22. And what that says is that the path starting here, going up to the root, plus the path starting here and going up to the root, if you combine those two, you get a path that has sum exactly 22. So essentially what we've kind of reduced the problem to is you're given an array of values. These are all of the path lengths starting at some node and going up to the root. Is there a pair of them that adds up to exactly 22? And you can solve this pretty easily in linear time using a hash table. So that sounds pretty straightforward, but there's actually a little bit of a hitch here. And that's that let's say you had something like oh, we have an example here already. Okay. Yeah, let's say that this particular branch didn't exist. You might be tempted to say, well, we have a 17. Oh no, no. Okay. We have a 17 here, and we have a 5 here. Their total sum is 22. So we found a path. But we've kind of cheated though, because this path actually goes from here, goes up to the root, then it backtracks on itself to go down here. And while yes, that's a path that has length 22, we can't do that. That's not a valid path. So you have to be a bit careful about that. So the way that you kind of have to do it is I guess there's a lot of different ways you could do it, but the way that I thought of is to say, okay, for each of these numbers, you calculate which, I guess, subtree it came from. So I guess if, let's make a slightly more complicated example. Maybe instead of like just 2 paths, the vertex we chose has like 4 paths. And each of these has their own subtrees with things going on in them. Who knows? They're doing some weird stuff. So for each of these paths that we calculated, we're going to record which of these branches it comes from. So maybe we call this branch 1, this branch 2, this branch 3, this branch 4. So maybe this one came from branch 1, this one also came from branch 1, this one came from branch 2, 3, 4, 2, and so on. And so when you're building this hash table, you make sure to be careful to record, I guess firstly, what values exist and in which tree or trees it came from. In particular, there's kind of 2 cases. Either a number appears exactly once, in which case you have to be careful because if the number you're trying to pair it with, in this case 5, here, happens to come from the same tree, you're going to get an invalid solution. So the numbers that appear exactly once are the ones you're most scared of. And the numbers that appear more than once, and in particular they appear in 2 different trees, you're much less scared of. Because now, because it appears twice, you know that if you try to match it, 17 and 5, together, it doesn't matter which tree this 17 came from, because whichever one it comes from, if it happens to be one that the 5, it happens to be the same tree as one of the 5s, you can just take the other tree. So that's one way you can get around this. Can't you just do each subtree in order and only update hash map after you've checked a subtree? Yeah, that's actually a much cleaner approach to do it. Yeah, but I guess there's a bunch of ways you have to get around it. You just have to be aware that that's a problem that might exist. That's a good point. Yeah, so does this idea make sense? So once you've rooted the tree, then the problem becomes really easy. If you're considering just all of the paths that go through this vertex, because they all have to, you're just trying to find, I guess, it's basically reduces to, given an array, can I find 2 elements of the array that have a sum exactly some value? Also, I guess it's worth mentioning the special case where k happens, there happens to be a path from some vertex to the root that already has sum exactly k. That's a special case that you might need to consider. Okay. So I guess now that you've answered the question for when this particular vertex we chose here is a part of our path, then what you can do is you can delete that vertex. And once you delete that vertex, oh God, that's horrible. Okay, maybe I'll do it down here. Once you consider all the paths that involve this root vertex, you can delete that vertex, and you don't have to worry about that vertex ever again, because you've already now considered every single path that goes through that vertex. So what you end up with is you're left with a bunch of isolated trees, and now you can answer the question of, does there exist a path of length exactly k in one of these trees? So that's kind of our solve the answer in our left side and our right side step, or the equivalent anyway of this particular when we're doing the problem on a tree. Applying divide and conquer on a tree, I mean. Okay, so any questions about this process so far? I guess importantly, it should make sense to you that we do end up considering all of the possible paths if we do this process of pick a root, find all the paths that go through that root and see if there's one that matches our criteria, and then removing that root from the tree and recursively solving on each of the remaining subtrees. Okay, cool. Now, the last important question is, how do we pick a good root? Because if we're not careful, we don't get this special order n log n nice time complexity that we had in our other examples. So for example, if you had a tree that was like just a line, something like that, and you picked like this leftmost vertex as a root, then once you erase this vertex, you're left with a tree that's only one vertex smaller. And if you keep getting unlucky and picking the leftmost vertex each time, then you end up having to solve the problem on order n trees. Each tree has order n size. So that's order n squared in the worst case, which is pretty terrible. So the answer, I guess, is you want to pick some vertex that kind of splits the tree in half each time. Formalizing that, you want to find a vertex. I don't know, you want to find a vertex, I think it's this one, where once you remove it, all of the subtrees that get left behind have size at most n on 2. That's kind of our equivalent of cutting the array in half. Exactly. So this vertex that splits our tree into a bunch of subtrees, and each subtree has size at most n on 2. First of all, such a node always exists, and second of all, it's called the centroid. Hence the term centroid decomposition. So in summary, you're looking for a vertex that proof by contradiction. Okay. This lecture is running a lot longer than I would like, so I'm going to omit the proof of finding such a vertex. You can read about it on the resources section in the problem sheet, which actually I think does a really good is a really good explanation of the centroid and centroid decomposition and stuff. But such a node always exists, and the way that you can find it is actually pretty straightforward. There's a couple of different approaches that I know of. I'm not sure which one is best to use, but the simplest one is to just go through all of the nodes and figure out which one is the centroid. So what you do is you need to be able to answer the question for each node, if I were to delete it, what is the size of all of the remaining subtrees that get created? If you can answer that, then you can easily figure out for each vertex what the size of the subtrees would be if you were to delete it. And if all of them happen to be size at most n on 2, then you know that you found the centroid. And proof by Google it later, the centroid will always exist. So how do you calculate the size of the subtrees as you delete them? The simplest way is to arbitrarily root the tree somewhere. And then do a simple depth first search to calculate the size of each of these subtrees. So, for example, the size of this subtree would be 3, would be 5, 7, 9, and so on. I think that's correct. And so, if you want to figure out what happens when you delete a particular vertex, well, you already know the sum of, already know the size of all of these subtrees that get left behind that are children of this vertex, and the size of, I guess, the remaining subtree that you get is just going to be all of the nodes that are left, excluding the ones that are in your children. So you can just calculate that with n minus the size of all of these. Okay, so root the tree somewhere, you calculate the size of all of the possible subtrees. You can use that to calculate for each node. If I were to delete it, would it be the centroid? And the answer is going to be yes for one of them. And once you found that, you can go over here and do this process of picking a root, of setting that as the root and calculating the answer for all of the paths that go through that root. Okay. Are there any questions on this particular idea? If not, then congratulations. This is pretty much all there is to centroid decomposition. It sounds really complicated, but it's actually a pretty, I guess, I wouldn't say straightforward, but it is just an extension of the divide and conquer idea that we discussed on an array. In fact, divide and conquer on an array is a special case of divide and conquer on a tree. It's divide and conquer on a tree, but the tree is a line. Okay, so I guess the last thing that that's kind of difficult here is how do you implement all this? It can seem a bit daunting because there are a lot of different parts to it, but all of the parts are relatively straightforward and they all come one after the other. I'll refer you to the resources section of the problem sheet because I think there's a pretty nice implementation mentioned there. Corollary of aforementioned proof? That doesn't look like it's spelt right. Anyway, okay. I know we're running close to time and there's actually more problems I wanted to get through. But I think for the sake of brevity, I'm just going to end it here. And maybe I'll have a second mini session sometime in the future if people want to go through more divide and more centroid decomposition problems. I don't know if this one particular example, it's kind of, I guess, a straightforward problem, but hopefully it explains what centroid decomposition looks like. There was supposed to be an RX set, but I haven't set it up yet. I'll do that after this session. But a lot of the problems, particularly the divide and conquer ones, are public AOO problems, I think. And there are plenty of problems that are from other sites as well. Okay. Any last minute questions before I finish off here? If not, then I think that's all. Thank you everyone for coming. Hopefully you all had a nice break between this lecture and the last set of lectures. There will probably be more lectures after this, continuing to go through some of the topics that we missed, and I would like to have like some more sessions on like just general problem session-y stuff, because I think that's something that we missed out a lot on during, like, I guess the April camp season of things. Mostly because, you know, there's a lot of content we're trying to get through, and trying to work out the logistics of this online April camp stuff has been pretty tough. Not to mention all the other, you know, general life and work things they have to deal with, and school things to do with the lockdown and stuff. But yeah, hopefully there'll be more sessions between now and the end of the year. And who knows, maybe we'll incorporate some of this more into the future, even after the lockdown is over. Alright, I will now end the stream. Happy training. I will get you your RX set at some point. If you if you're someone who hasn't who wasn't at April camp, I'm not sure if there's any people in that boat. Ping me your ORAC username if you have one, then I can add you to the set. Okay.